We're now ready to begin using software to fit and test hypotheses about structural equation models. In this lecture video, we'll see how to use the CALIS procedure in SAS to fit structural equation models. We'll do this in the context of an example, in particular a confirmatory factor analysis modeling example. Here's an outline of what we'll be looking at in this video. We'll first review the steps involved in specifying a structural equation model. Now, we looked at these steps previously, and we're going to review them again because it is these same steps that we use when we specify a model using SEM software. Once we've done that, we'll fit the SEM for this confirmatory factor analysis using SAS PROC CALIS. So let's take a look. So we're going to be doing this in the context of a confirmatory factor analysis. Here's a description of the example. Consider a confirmatory factor analysis to assess the relationships among a person's ability, their achievement motivation, and aspiration. These three characteristics are considered to be latent, that is, unobservable constructs or factors. Now, it is proposed that three manifest variables are indicators of ability, three manifest variables are indicators of achievement motivation, and two manifest variables are indicators of aspiration. Data were collected on 250 second-year college students. The next slide shows the data collected for use in the study. So here are the variables that were collected for use in the study. There were three ability scores, consisting of a general ability score, and then two grade point averages. The first, the grade point average in the last year of high school, and then the grade point average in the first year of college. There were also three achievement motivation measures, and finally, there were two aspiration measures, an educational aspiration measure and a vocational aspiration measure. We do not have access to the raw data, but we do have the sample covariance matrix, denoted by bold S, which was computed from the raw data. We also have the number of observations obtained for each variable. The sample covariance matrix and the sample sizes are actually all we need in order to fit and test hypotheses about the structural equation model. In a sense, then, a sample covariance matrix, along with the sample sizes for each variable, can be considered to be the raw data for a structural equation model analysis. Now, all variables were measured for each student. There were no missing values for the variables for any student. As stated previously, the number of students on which data were collected was 250. The sample covariance matrix, computed from the raw data, is shown on the next slide. So here we have the sample covariance matrix, bold S. It is an 8x8 covariance matrix, and because covariance matrices are symmetric, we only need to display the entries on the lower portion of the matrix. Next, let's review the steps involved in specifying a structural equation model. Step 1. Identify all latent constructs or factors and manifest variables comprising the SEM. Step 2. Specify an equation for each one-way, explanatory, predictive relationship in the SEM. Step 3. Specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables. Step 4. Identify and count the number of model parameters that need to be estimated. Step 5 is to construct a path diagram for the SEM. And then finally, we'll add a sixth step where we fit the SEM using SAS. So let's look at step 1. Identify all latent constructs and manifest variables comprising the structural equation model. there are three latent or unobservable constructs, also called factors. We'll denote them by F1, F2, and F3. F1 represents a person's ability, F2 represents their achievement motivation, and F3 represents their aspiration. There are 8 manifest or observable variables, which we will denote by V1 through V8. V1 represents a general ability score. V2 is the student's GPA in the last year of high school. V3 is their GPA in the first year of college. V4, V5, and V6 are achievement motivation scores 1, 2, and 3 respectively. V7 represents a general educational aspiration score. And finally, V8 is a general vocational aspiration score. Next, we need to identify which factors each of the manifest variables is associated with. So V1, V2, and V3 are associated with the first latent construct, F1, which is the student's ability. Manifest variables that are indicators of the latent construct achievement motivation, or F2, are the 3 achievement motivation scores, V4, V5, and V6. The manifest variables that are indicators of the latent construct aspiration, or F3, are the 2 aspiration scores, V7, the general educational aspiration score, and V8, the general vocational aspiration score. Next, let's look at step 2, specifying an equation for each one-way, explanatory, predictive relationship in the SEM. The equations involving the ability factor F1 are as follows. V1, which is the general ability score, is equal to lambda 1 times F1 plus its own error term, E1. V2, which is the GPA in the last year of high school, is equal to lambda 2 times F1 plus its own error term, E2. And finally, V3, which is the GPA in the first year of college, is equal to lambda 3 times the ability factor F1 plus its own error term, E3. The equations involving achievement motivation are as follows. V4, which is the first achievement motivation score, is equal to lambda 4 times F2 plus its own error term, E4. V5, which is the second achievement motivation score, is equal to lambda 5 times F2 plus E5, its own error term. And then finally, V6, the third achievement motivation score, is equal to lambda 6 times the achievement motivation factor F2 plus its own error term, E6. And finally, the equations involving the aspiration factor, or F3, are as follows. V7, which is the general educational aspiration score, is equal to lambda 7 times the aspiration factor F3 plus its own error term, E7. V8, which is the general vocational aspiration score, is equal to lambda 8 times F3 plus E8, its own error term. And so here we have all of these equations on one slide. These are the regression type of equations that comprise the structural equation model for this confirmatory factor analysis. Now note that the SEM includes equations relating the factors to the manifest variables they impact. Each of these equations is regression-like. Note, however, that there are some differences between these equations and the regression equations we've seen in other courses. In particular, note that in each of these equations, everything on the right-hand side of each equation, an example of which we can see below, is either an unknown constant or an unobservable random variable, that is either a factor or an error term. So the right-hand side of this equation, VI equal to lambda I times F sub j plus E sub I. The lambda sub I is an unknown constant, and both the factor F sub j and the error term at E sub I are both unobservable random variables. And so the entire right side of that equation is unknown or unobservable. Now this is different from a typical fixed effects regression equation, which has one or more observable explanatory variables on the right-hand side. In step 3, we specify notation and or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. In this model, all error terms are assumed to be pairwise uncorrelated. This is represented notationally in the following way. The covariance of E sub I and E sub j is equal to 0, where I is not equal to j. Note that this assumption imposes values on 28 covariance parameters. Each error term will have its own variance, at least initially. Hence, we will define separate notation for the variances of each error term as follows. The variance of E sub I, which is the covariance of E sub I with itself, will be denoted by theta sub I for I going from 1 to 8. Next, latent constructs and error terms are assumed to be pairwise uncorrelated. This is represented notationally in the following way. The covariance of F sub I and E sub j is equal to 0 for each I going from 1 to 3 and j going from 1 to 8. Now note that this assumption imposes values on 24 covariance parameters. The latent constructs are allowed to be correlated. Therefore, we need to define notation for these covariances. And the notation we'll use is as follows. The covariance of F sub I and F sub j, the ith and jth latent factors, will be denoted by cap phi sub ij, where I is strictly less than j, I is greater than or equal to 1, and j is less than or equal to 3. And so this sets up notation for 3 covariances. And then finally, for identifiability purposes, the scale of each latent construct will be set to a unit variance, that is, to a value of 1. And so we can represent this notationally as the variance of each F sub I is equal to 1. Next, in step 4, we identify and count the model parameters that need to be estimated. So first, we have the loadings, the lambda sub i's, which are the coefficients in those regression type relationships relating the manifest variables to their factors. And so we have 8 parameters there. We also have the variances of the error terms, the variance of E sub I being denoted by theta sub I going from 1 to 8, and so we have 8 more parameters. We have the covariances between the factors. So the covariance of F1 and F2 is denoted by cap phi sub 1, 2. The covariance of F1 and F3 is denoted by cap phi sub 1, 3. And finally, the covariance of F2 and F3 is denoted by cap phi sub 2, 3. And so we have 3 parameters there. And so there are 19 parameters that need to be estimated in order to fit this structural equation model. Now let's also calculate the model degrees of freedom. This is going to provide a useful check once we've fit the model, and we can use this to help ensure that we have fit the model correctly. So the number of manifest variables is equal to 8. This is denoted by P. The number of parameters to be estimated, which we denote by Q, is equal to 19 in this case. And with those, we can calculate the number of degrees of freedom associated with the model. The formula for the model degrees of freedom, you'll recall, is P times P plus 1 over 2 minus Q. So we have 8 times 9, or 72 over 2, which is 36, minus 19, and so we have 17 model degrees of freedom. Step 5, we construct a path diagram. Now on the path diagram, we will also identify the latent constructs, the error terms, the endogenous variables, as well as the exogenous variables. By identifying and classifying these variable types before fitting the model, and then comparing this list with the output from the software, we'll be able to help verify that the model has been fit correctly in the software. So you'll recall that in a path diagram, ovals or circles are used to represent latent constructs. We've got 3 factors in this model, so we'll have 3 ovals or circles in our diagram. Rectangles or squares are used to represent manifest variables. We've got 8 manifest variables in this model, and so we'll have 8 rectangles or squares in our diagram. There are 8 error terms in this model, 1 error term for each response type variable, one for each type of regression type of relationship in the model. And these error terms will be represented in the diagram by their respective letters. One-sided arrows are used to represent relationships that are one-way, directional, or predictive. Two-sided arrows are used to represent relationships that are two-way, correlative, or mutually impacting. And finally, parameters to be estimated in the model are indicated in the diagram by asterisks. And so here is the path diagram for our model. Let's identify the latent constructs or factors. We have F1, F2, and F3, the 3 factors which are indicated here by ovals. The manifest variables, variables that are observable, are V1 through V8, as you can see here. The error terms are denoted by E1 through E8 in the diagram. Endogenous variables are variables that are response variables in any of the equations in the model. And so in this model, the endogenous variables are V1 through V8. On the other hand, exogenous variables are variables that are never response variables in any of the equations in the model. And so the exogenous variables are the latent constructs F1, F2, and F3, because neither of those has a one-way arrow coming into it, as well as the error terms E1 through E8. Again, none of those terms has a one-way arrow coming into it. And finally, step 6. Let's take what we've put together so far, this information that we've collected, and let's fit the SEM for this confirmatory factor analysis using SAS PROC CALIS. Now, CALIS is an acronym for covariance analysis and linear structural equations. Now, again, we do not have access to the actual raw data, but we do have the sample covariance matrix, which was computed from the actual raw data. We also know that the number of observations obtained for each variable is 250. The sample covariance matrix is given on the next slide. Now, because covariance matrices are symmetric, only the lower triangular portion needs to be shown here, and in addition, only the lower triangular portion needs to be specified when creating a data set containing this covariance matrix in SAS. So the first step is to create a SAS dataset containing the covariance matrix of the manifest variables. Here is the SAS code to do this. First, the data statement creates a SAS dataset, which in this example, we are giving the name COV. We could call it anything we like, however. Now note that when creating a covariance matrix using a data step, we must specify the type equal COV option in parentheses. Now note that in this context, the missing value dots represent values that are equal to their cross-diagonal counterparts and therefore not explicitly entered into the data set. I suppose we could enter them, but it just requires more typing, so we don't have to do that. But the dots cannot be left out. Notice that in addition to the values in the covariance matrix, we've also included a row giving the number of observed values for each variable represented in the data set. Now, in this particular example, every variable was measured on each of the 250 students, but it is possible in many situations that there may be some missing values for certain variables. And so in a situation like that, in that last row where that has a sample sizes, you could have different values for the different variables in that row. Next, let's look at how to specify the structural equation model in SAS PROC CALIS. Now, PROC CALIS is very general and very powerful structural equation modeling software. PROC CALIS provides several different programming styles, or programming languages, if you will, for specifying structural equation models. And these different languages correspond to the different types of SEM software that is out there. Now, in this lecture, we're going to be using what is called the LinEQS modeling language, which is modeled after the language in the EQS SEM software package. There are three main statements that we will be using to specify the model in PROC CALIS using the LinEQS modeling language. The LinEQS statement to specify the algebraic equations in the model, the variance statement to define notation and specify values for variances in the model, the COV statement to define notation and specify values for the covariances in the model. We will also issue the path diagram statement that will instruct SAS PROC CALIS to construct a path diagram for the fitted model. So the first statement we see, PROC CALIS data equal COV. This statement invokes the PROC CALIS procedure and tells the procedure the data set to use. Then we have the LinEQS statement. And notice that there's no semicolon right after that. We have a list of equations. The LinEQS statement is used to specify the regression type relationships in the SEM. Now, there can only be one LinEQS statement in a PROC CALIS invocation, and all of the regression type relationships in the SEM are entered in that one LinEQS statement. And the different equations are separated by commas. And so in this example, we have LinEQS, and then the first equation, V1 equal to L1, which represents lambda 1, times F1 plus E1, and then a comma, V2 equal to L2 times F1 plus E2, and then a comma, and so on down to the last equation, V8 equal to L8 times F3 plus E8. So notice that all of those equations are separated by commas. Also note that there is no comma after the last equation. That would generate an error, but we do have to have a semicolon after that last equation. Here we have the variance statement. The variance statement is used to define names for variances to be estimated and specify the values of variances that are set by model assumptions and/or identifiability considerations. And so you see here that the variances of the latent constructs, F1, F2, and F3, for identifiability purposes, are each set to the constant value 1. Because they're set to 1, they're not going to be estimated from the data. The last several lines are the variances of the error terms E1 through E8, and it is there that we give them names. So the variance of E1 is denoted by var underscore E1. The variance of E2 is equal to or defined to be represented by the label var underscore E2, and so forth down to the last one. And so we are assigning variable names to these variances, and because of that, their values are going to be estimated. And finally, we have the cove statement. This is used to define names for covariances that need to be estimated, and also specify the values of covariances that are set by model assumptions and/or identifiability considerations. Now, there are potentially a lot of covariances in any given SEM. By default, and for convenience, in the CALIS procedure, covariances are set to as value of 0 unless they have been assigned a name. In that case, they would be estimated, or set to another non-zero value. Now, this is very convenient because it greatly reduces the number of covariance values that need to be explicitly set in the covariance statement. So as you can imagine, if that was not the default, we would have to assign, if there were a lot of covariances equal to 0, we would have to explicitly set those covariances equal to 0. But by default, they are 0 unless we tell PROC CALIS otherwise. And finally, we have the path diagram statement. Now, this statement is not used if we're wanting to fit the model, but it is a good idea to include this because once we fit the model, if we have PROC CALIS generate a path diagram, we can compare that path diagram to the diagram that we constructed by hand before we did this. So you'll recall that we constructed the path diagram. I did that in using presentation software, but that's certainly not necessary. Really, all that would be necessary would be to draw it by hand on a sheet of paper. Now, this is a very simple statement, as given here, path diagram and then a semicolon, but there are options available that modify the diagram produced. And so here's the full specification for the initial modeling run. All right, now let's look at the results of the initial model fitting. And so as a first step, what I've done is print out the COVE data set so that I can verify that it was input correctly. And I can compare this to the slide that I constructed previously, and we can make sure that all of those covariances and the sample sizes are as they should be. Next, it's a good idea to look at the modeling information table and the table showing the variables in the model. And so this modeling information table shows that the analysis is based on 250 observations, that the modeling language or the model type is the LIN-EQS model type, and that we're doing an analysis of the covariances. As far as the variables in the model, we see that we've got 8 endogenous manifest variables, V1, V2, and so forth, up to V sub 8, and we know that to be true. That's one of the reasons for listing those before we even get into the software, right? So that we have all of this information that we can compare to the output once we have fit the model. We also see that we do not have any endogenous latent variables, nor do we have any exogenous manifest variables, but we do have 3 exogenous latent variables, F1, F2, and F3, and we also have 8 exogenous error variables, E1 through E8. And so we have 8 endogenous variables and 11 exogenous variables, and that matches up with the list of variable types that we looked at before we got into the software. Next, we look at the fit summary table. Now, this is a fairly long table in the output. This shows the very first part, the modeling information. And so we see here that we have 250 observations upon which this model is being fit. In addition, we have 8 variables, 8 manifest variables in particular, and we have 19 parameters to be estimated. That agrees with the counts that we came up with previously. Next, we have the absolute index, part of the modeling fit table. And in particular, we see here that we have 17 degrees of freedom. And this corresponds to the number of degrees of freedom that we calculated by hand previously. Now note also that the chi-square value associated with this model is 20.5813. We're going to use this later in testing hypotheses via model comparison. Next, we have the effects in linear equations. And so these are the point estimates of the loadings. And so we see that the point estimate for lambda 1 or L1 is 0.51880. The point estimate for L2 is 0.61477. The point estimate for L3 is 0.52147. The point estimate for L4 is 0.51137. The point estimate for L5 or lambda 5 is 0.59351. The point estimate for L6 is 0.59527. The point estimate for L7 is 0.61434. And finally, the point estimate for L8 is 0.63483. Next, we have the estimates for the variances of the exogenous variables. Now, notice at the top that in the estimate column, for F1, F2, and F3, there are 1s. Now, those are not estimated from the data. You'll recall that we set those equal to 1 in the variance statement. Underneath that, we have the variance estimates for the error terms. And so you can see here that the variance for E1 is estimated to be 0.18085. The estimate of the variance for E2 is 0.18206, and so forth. Next, we have a table that gives us the covariances among the exogenous variables. And so the covariance between F1 and F2 is estimated to be 0.63643. The covariance of F1 and F3 is estimated to be 0.27638. And the covariance of F2 and F3 is estimated to be 0.68099. And finally, we have a path diagram of the initial model. Now note the double-sided arrows attached to each error term. Recall that double-sided arrows represent covariances. Recall also that the covariance of a random variable with itself is equal to its variance. And so these double-sided arrows associated with the manifest variables represent the variances of their error terms. Notice also that this path diagram does not have double-sided arrows representing covariances between pairs of factors. But if you think back to the diagram that we created previously by hand, we did have double-sided arrows between those latent constructs, right? Because we want those latent constructs to be, we allow them to be correlated. And in the program itself, we define notation for the covariances between each pair of latent constructs. But even though the double-sided arrows are not displayed in this diagram, the covariances have been estimated. In fact, on a previous slide, we saw what those estimates were. So the default in the path diagram statement is to not show the double-sided arrows between the latent constructs, but you can have them added, and we'll see how to do this in a subsequent lecture. So to summarize, the confirmatory factor analysis structural equation model has been specified to PROC CALIS using the LinEQS programming language. The model has been fit, the parameters have been estimated, and all indications are that the model has been specified correctly. And so the next step would be to test hypotheses about the parameters in the model. But that's going to have to wait until the next lecture video. I'll see you then.